Hey, linear algebra. This is the class that would take place on Wednesday, September 22nd, 2021, in which we will cover section 1.8 of the book. 1.8 is called Linear Transformations, and I am going to pull up the whiteboard now. So we have section 1.8, which is called Linear Transformations. What are they? Well, it's a kind of function from vectors in n-dimensional space to vectors in m-dimensional space. So a function. Yeah, so you're going to hear dogs in the background. Dogs are crazy today. So a linear transformation T from Rn to Rm, this is notation, is a function. Now remember that a function is a rule which has inputs and outputs, where the inputs are all vectors in Rn, and an output, each input gives an output, is a vector in Rm. So it's a rule. Think of it as a machine. You stick in a vector in Rn and out pops a vector in Rm. That's what it means to be a function. And then the conditions of being linear are the following two conditions. T of x plus y equals T of x plus T of y. That's the first condition. And the second condition to be a linear transformation is that T of C times x, where C is any scalar, is C times T of x. So these are the linearity conditions on the function, making it into a linear transformation. Now, you've actually seen linear transformations already, but in a different form. So here's the main example. Let A be an M by N matrix. Remember, that means the number of rows is M, and the number of columns is N. So I claim that an M by N matrix gives you a linear transformation from Rn to Rm. And here's the definition, define. So this is going to give rise to a linear transformation T from Rn to Rm, where T of x, what can I do to x? X is a vector in Rn. I can form the matrix product A times x. X is a column vector here. So this will be, remember, A is M by N and X is N by 1. So A times X is going to be an M by 1 matrix, and that's therefore an element. This is an element of Rm. Okay. So here's a very, very concrete example. So let A be the 1 by 2 matrix, 1, 2. And so therefore, this is 1 by 2. So M is 1 and N is 2. And it's supposed to define T going from Rn, which is 2 in this case, to R1. And T of a two-dimensional vector, let's say the two-dimensional vector is xy, T of xy is going to be given by 1, 2 times xy, and we form the matrix product. That's going to be the dot product in this case. It's going to be 1 times x plus 2 times y which is x plus 2y. And now I claim that linearity is satisfied. The linearity conditions are satisfied for the matrix product, and that's because we saw that A of x plus y for sum of vectors. A preserves sums of vectors, A of x plus A of y, and A preserves, you can move scalars through A. So AC times x is C times AX. And that guarantees that the linear transformation, T is a linear transformation, these two conditions. Okay, so, right, I want to sort of define now some terminology, which you've seen in other contexts. So T is going to be a linear transformation from Rn to Rm. The set of inputs, that is all vectors in n-dimensional space, Rn is called the domain of T. Rm is called the target, or sometimes called the codomain of T. And now there's one other thing we want to say is that the set of all elements of the target of Rm, which are of the form T of x for some x, the set of all these elements inside Rm is the range or the image of T. So that's the third notion, that the image or the range. So we have the domain, we have the target, and we have the range. All right. So I think we're going to just talk mostly about examples now. So here are some examples. So let's consider T going from R2 to R, given by T of x equals, just is always the zero vector for any x. So T of x is 0. That is a linear transformation, as you can check. And its domain is equal to R2. Its codomain is equal to R1, or the target is R1. And the range, or the image, is given by the set of all vectors of the form T of x. But T of x is always 0, so T of x is 0 in which is in R1. A vector in R1 is just a scalar, right? So it's just 0. The range is 0. Okay. So that's the first example. Here's a different example of a linear transformation. It's something called a projection. So let's define T going from R2 to R by T of a two-dimensional vector, xy is going to be, let's just say, y. So this is called the projection onto the y-axis. So this is the y-axis projection. It is elementary to check that T preserves sums of vectors and scalar multiplication. So it's a linear transformation. And this is called this is a projection. You could also define, that's the y-axis projection is also an x-axis projection. T of xy equals x. That's the x-axis projection. Okay, so that's an example of a linear transformation. More generally, there's a linear transformation from if k is less than n, we have a linear transformation from Rn to Rk, which sends t of x1 all the way up to xn. I just select the first k entries in the vector and form a column vector from it. And this is pretty clearly a projection. It's a projection. We think of this as a projection onto the first k coordinates. That's what we can think of it as. And this is a linear transformation. It's preserves sums of vectors, and you can move scalars through it. Okay, so this is that's it for projections. So let's talk about a different kind of linear transformation. It's an example of something called a distortion. The book calls it something else. The book calls it a shear transformation. So what's an example of a shear transformation? So let's let A be the matrix 1, 2, 0, 1. And as before, this defines a linear transformation, in this case from R2 to R2, in which T of xy is given by 1, 2, 0, 1 times the column vector xy. That's a linear transformation. And what is this going to be given by? Well, we can compute it by computing the matrix product. You're going to get 1 times x plus 2 times y, which is x plus 2y. And we're going to get y here. So now, why do we call this a distortion? We'll see it as follows. Let's consider the unit square consisting of vertices 0, 0, 1, 0, 1, 1, and then 0, 1. And let's see what the linear transformation does to these three vectors in the unit square. So let me erase this vector here. So what is t? What is t of 0, 0? That's given by 0. So use the formula for t, x plus 2y, y. We get 0 plus 2 times 0, which is 0, and then 0. So you get the 0 vector. So let's see what t does to the unit square. Okay, so you're going to get 0, 0 goes to 0, 0. What about the vector 1, 0? What does t to do to the vector 1, 0? So t of 1, 0, I'm running out of space, but t of 1, 0 is going to give me 1 plus 2 times 0, comma 0, so it's 1, 0. So it preserves 1, comma 0. So I'll plot that point, 1, comma 0. Okay, and I'm going to erase these matrices. Okay, and now let's go see what t does to 1, comma 1. Oops. T of 1, comma 1. Let me work on top here, and I'm going to do it in a different color. So t of 1, 1 is going to be 1 plus 2 times 1, and then 1. So that's 3, comma 1. The vector 3, 1. And so if we plot that, let me plot these things in blue. If we plot that, we get 3 units out, 1, 2, 3, and then 1 unit up, so that you get this you're plotting this point here. And then lastly, what is t of 0, 1? The last vertex of the square. Well, t of 0, 1 is, you can compute it, you'll get 2, 1. And what is 2, 1? You go 2 units out and 1 unit up. And if you join these lines together, you see that the unit square gets mapped using T to a parallelogram. So we're distorting. In fact, you can think of like a person, think of a person standing in the unit square. What happens to that person is that person gets distorted. So that's why I call it a distortion, right? The person's, you're taking the unit square and slanting, you're making the vertical edges, you're slanting them so that they become a parallelogram. And what happens to the person sitting in the unit square? That person gets distorted. So that's an example of what is called a distortion or a shear transformation. Okay. So what I'm going to do now is I'm going to discuss some additional properties which are pretty obvious of linear transformations, but I should mention them. So suppose I'm given a linear transformation, T from Rn to Rm, and then, so this is the fact, then T of the 0 vector is always the 0 vector, and T of A times X plus B times Y. So these are scalar multiples of X and Y added together is A Tx plus B times Ty. Okay, so let's see why this is true. So let's call this 1 and let's call this 2. And let's give a proof. So the proof of 1 is T of 0. Now the 0 vector is also, you can multiply it by 0, the 0 vector, you still get the 0 vector. But now T, we can move scalars through T. So that's 0 times T of 0. And then if I multiply any vector by 0 as a scalar, I get the 0 vector. So that handles property, the first claim. And the second claim, well, T of AX plus BY is by the linearity of T, you get T of AX plus T of BY. That's the first part of the linearity condition. And then the second part of the linearity condition says that T of A times X is A times T of X. And likewise, you get B times T of Y. And that's what we have to show. So we've actually established the two properties we are claiming. Okay, so the last thing I want to do, and this is a very short lecture today, is discuss one more example of a linear transformation that's in the text, which are called dilations or contractions. You can do this for any Rn, but let's just do this for R2. So let R be greater than or equal to 0, be any scalar. Let it be strictly bigger than 0. So, so consider, yeah, that was an interruption of the dogs. So we fix a scalar, R, like think 2 or a half, and we define a function from R2 to R2 by T of XY equals twice. Let me do it without specifying a matrix version. Let me just say T of X vector X is R times X. Scalar multiplication. Okay, so for example, First of all, this is a linear transformation because t of x plus y, the sum of two vectors x and y, that's r times x plus y. And then this is one of the properties of scalar multiplication. It's rx plus ry. And t of c times x is going to be r times cx. But this is the same as c times rx by one of the properties, the other property is scalar multiplication. So that's going to be ct of x. Okay, so for example, let's let r equal 2. What is this actually doing? So that's t of x in this case is twice x. It's stretching any vector in R2. It's stretching it by a factor of 2. So here I'm stretching each vector a factor of 2. And it points in the same exact direction, but it's just stretching. So that's a dilation. And we have the example of r equals 1/2, and that's going to shrink. It's going to shrink vectors to half their length. So this shrinks x to half its length. So this is called a contraction. And I won't try to draw that because it gets messy, the picture. Okay, so that's all I want to discuss today. We've finished section 1.8 of the text, and we will continue live in person next time on Friday. And I'll also release some review questions by that date. Okay, so have a good one.